So the first speaker is James Syvitski, Executive Director of the Community Surface Dynamics Modeling System at the University of Colorado, Boulder, and therefore probably feeling very much at home here, and Chair of the International Geosphere-Biosphere Program.
Thank you. It was 63 degrees in Boulder yesterday. So there's so many ways you can talk about rivers in the Anthropocene, and I'm going to give you my spin on it. And well, I should say, first off, what you're looking at here is a map. It's from a model. It's of the suspended sediment concentration of rivers in a part of the world, South America, without any human interference. So we have developed models that can take us back to when humans weren't around. And it is fascinating, if you're a geoscientist, to remember those days. But we can introduce humans into the equations and look at some of the results. And this diagram shows the difference in percentage between disturbed minus pristine when humans had little impact. And the climate period was 1981 to 2010, because you need climate to drive these models. And this is a very conservative diagram. The effects are probably much larger. Where you see blue in the river systems, that's showing that there's large dams that are filtering out sediment. And where you see red, you're seeing areas of the world where humans are still messing up with the soil, deforestation, and other things like that. And they're liberating a lot of material into the river systems. And in the lower part of the diagram, you'll see that there's the Aswan Dam. Dirty water enters the dam, as in the satellite image to the right, and in the model run, and out comes clean water. Very anthropogenic. This is an interesting little movie. Each image is from 1 year, from 1984 to the present. It's from one of these pristine areas. It shows what rivers should be doing. It shows we can learn a lot from pristine rivers, but there aren't many pristine rivers left, so we better get out and study them soon. For instance, in this diagram, there's a town in the Amazon that was growing in size. You'll see it in the middle left. And you'll see how it is a fixed point. So we've introduced fixed points into the river system. They could be levees, they could be towns, they could be structures. And this is a set of satellite imagery of gold mining in the Amazon, where you can see the hill slopes just devastated, liberating just so much sediment that the river system itself is overwhelmed, and you have a new river system. So many aspects of human endeavors are impacting, and in this case, impacting either the flow of water or the amount of sediment that the rivers move. So this tiny river example from Taiwan, the Linyang River in northwest Taiwan, or northeast Taiwan. There's a diagram on the lower part of the slide. It's a mass diagram, cumulative sediment load versus cumulative discharge. And in a pristine world, it would plot along one line. And you see this river system plotting from 1950 to 1960, 1959 on a line. And that's the way it should work. And then you'll see this impact of a large superhighway they put in, road construction. And so it liberated a lot of sediment, and so you had a change in that, a kink in that curve. And then from 1963 on to 1979, you'll see a new trend line where it recovered. But you'll notice it didn't quite recover to where it was. That's really important. There was more road construction. It then recovered again, but it really didn't recover to where it was. So we're changing the equilibrium status. We don't just perturb the system, we change it from then on, so that when a typhoon hits, all hell breaks loose. And we do this many ways. That was an example from road construction, but there are many ways we've impacted the river systems of the world. One of them is deforestation, cutting or burning. The two pictures that I took from New Zealand of landsliding or gullying, they show the impact of deforestation in New Zealand. And the diagrams shows both observations from river systems and lake systems versus a model. And both are showing the same thing, that the Europeans that went to New Zealand really strongly impacted during the Anthropocene the fluxes out of that river system. The nice thing about the Great Acceleration suggests that if you went back 150 years ago, you would find maps that we've produced on river systems that show what these river systems might have been like without this big human footprint. So in the Indus, as these two show, from 1829 and 1922, you can see the system and how that river was behaving before humans started messing it up. In this diagram, it shows the channels mapped out through a few of the years. And you can see that on the most extreme left, you will have natural spillways where during floods the water would flow out into the desert system. On the right is the modern world. Instead of having copious distributary channels that go to the ocean, you only now have one. Instead of having these natural spillways, you have more than 30,000 kilometers of irrigation canals. And these canals are functioning because of the barrages we put right in the river systems themselves, moving out the water and the sediment to the margins. Many times, the deltas of the world today are because of humans. If it wasn't for humans, we wouldn't have some of these deltas. The Po River, in this case, is a wonderful example. You can see that in the 10th century BC, from historical maps, that the rivers would move around to such an extent that the wave energy, tidal energy, would be able to handle that flux of material. There were no deltas. 10th century, you'll notice that the rivers reorganize. And that's the thing about natural rivers. They want to reorganize all the time. In the 16th century, the people of Bologna wanted a shipping route to go to Venice, to take their goods to Venice. So they commandeered some of the natural spillways and changed them into a more permanent system. And you ended up with the modern Po River itself. The Venetians were very upset. They did not want their lagoon filling up with sediment, so they made the Bolognese to construct the Pila Channel, which eventually led to the Po River Delta as we know it today. And as I said, these rivers love to move around. So in the Yellow River, you'll see that it used to migrate over a 700-kilometer wide floodplain. And the Chinese, with their very capable mapping abilities, we know exactly where these river channels were. Not only that, the remnants of these river channels show up well in our satellite images. So we precisely know the magnitude and location of these channels. So for the longest time, it was flowing into the Yellow Sea, the Yellow River flowing into the Yellow Sea. Now it flows into the Bohai. But during that time, 15th, 16th, 17th century, the Emperor of China wanted to stop the Yellow River from migrating. They spend 10 to 15% of their gross domestic product trying to keep the river from moving. This is a sad but interesting story. And it's actually, at some level, kind of funny. So on these two images, which are topographic images from satellites, SRTM, you will notice that these rivers, the yellow, the old Paleo-Yellow River, you can see in section C there. So this is a river that no longer functions today. There's no water flowing there. It's just the remnant. It's super elevated. So the engineers from China, the 15th to 18th century, super elevated this river by putting in levees. The levees trapped the sediment. You had aggradation, and you started to develop a super elevated river, where the river channel is up in the sky compared to the floodplains. And the 18th century one there, this is P3, if you want to go back to that. You see the line, that's P3, and you'll see P2. So this is the historical 18th century. Because of levees, we ended up piling up sediment in a flat plain. And you'll see the modern one, because we now use cement, it looks slightly more anthropogenic, I guess. But what is the consequence of this? This is a failed experiment. You'll notice that, another little tidbit, the Chinese kept meticulous records of where floods were, how long the floods lasted. You know, was it a week, a month, a year, 2 years? What was the cost and the magnitude of the size of the repairs of the levees? Anyways, it led to the following diagram. And you'll notice along that 15th to 18th century channel that the magnitudes of the flood were really large. Well, it wasn't a particularly wet period. It was just that you had engineering failure during that time. So we created larger floods in that area of the world. So let's move on to water discharge. It's quite common today to have a river system with, let's say, 100 units of water. In this case, it's cubic kilometers, but it doesn't really matter what the units are. 100 units moving in, 40, 50 units getting to the sea. Where does the water go? It goes into, in this case of the Indus, it goes into the ground, it goes into the crops, it goes up in the sky through evapotranspiration, goes to cities and things like that. My colleague John Milliman, he produced this diagram of changes of from the 1950s to the modern period. And everywhere you see a large red dot, the discharge has decreased by more than 30%. Water discharge. And because you're taking the water that used to get to the sea and you're relocating it for different reasons. But the consequences are huge. And this sad story you will see both in water and in sediment load. It's been going down, 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 down. And now you have virtually no water or sediment getting to the coastal ocean. So if you were humans living on the delta, you are now facing salinization of your soils, etc. And unfortunately, this is one of the more poorly respected parts of Pakistan. So those folks have had a hard time. But this modern decrease, because of dams and things like that, is worldwide. So the Yellow River, you can see the same downward trend, where 50 years ago, it put out around 1,500 million tons per year, and now it's putting out only 150 million tons per year, an order of magnitude change. So we elevated the flux of sediment through soil erosion, deforestation, in this case on the Lusk Plateau, but we're also today changing the cycle, but we're changing it for reasons that were different from how we caused it in the first place. And if we bring it back home to the US, nothing's different here. Colleagues of mine, Bob Mead and John Moody, they produced this wonderful diagram of the fluxes of sediment to the coastal ocean, Gulf of Mexico, where in their estimates, it was around 430 million tons per year at one time, and now it's 240. And in fact, the latest numbers, it's around 150. So we're reducing the flux. And that, in part, is because of some of the damming activities that has gone on. So I have a Matrix movie. I think you'll like this. Some of you have seen it, but I never tire of it, so I hope you don't. So what you're going to see is the placement of a dam from the National Inventory of Dam. And the clock is on the upper part of the diagram, and you'll see it tick for every year. So you'll see the European migration across the country. And if you were to take a box like that, blow it up, most of the water you see there are reservoirs. There's almost no natural lakes there except those little tiny lakes, meander loop lakes around the Mississippi. And if you were to blow it up more closely, you would see that you have the blue is showing the suspended sediment entering the reservoirs and not leaving. And just so that if you're from another part of the world, you can see this. These are the giant dams. These are the 45-meter plus height dams of the world, so there's fewer of them. Check out 1953 Mao Zedong in China, and you'll see a flash. And you end up with the impacts. You lose, in this case on the Nile, you lose the maximum discharge, you decrease the average discharge, you end up with subsidence, erosion on the coast. Our river systems in Italy, the lower diagram shows monthly flushes. We actually have river systems that look like toilets. We flush them every month, more or less, same time of the month. We have floods like in Thailand, that all the red areas is flooded lands of the valley, and that was created by humans not wanting the dam to be overtopped. They let the water go, they caused the flood themselves. So if you look at the Dartmouth Flood Observatory data, which is a unit within CSDMS, we map out the flood magnitudes, but we're pretty convinced that many of the increases are because of human action, not an intensification of the hydrological cycle. We have, I wrote a paper recently about the flood of 2010 on the Indus, and you're going to see an amazing movie now. So here, this flood of 2010, you can see the Indus flooding. The barrage is right there. And then you'll see it broke its levee system. You had an avulsion. And you'll see it move across the landscape. And so there's a 100-kilometer scale just for you to, and every day you're going to see a new one of these images tick on by as this flood water comes down. This was totally because of humans. Not, I mean, yes, it was a rain and monsoons, but it's a total human caused flood. So let me come to an end and just say that that is an example because of human decisions that 20 million inhabitants were displaced, 2,000 people died, and I leave you with welcome to the rivers in the Anthropocene. Thank you.